Hello, we can start. Yeah,
Yeah, you can start. Sure.
yes, please. Thank you.
Okay.
So in the first step, we just learned that how to analyze the size of the particle, and we are familiar with the few advanced features or the or you can say the few acronyms. So in this session, actually, we will learn about the Zeta potential and the few another few the acronyms, that is the M3 or the pulse, right? So we measure the size of the particle. Now we are happy, but after 1 day or 2 day or after some time, when you are going back to again analyze the size, you are not getting the actual the exact data whatever you have uh, gave in the previous. So that means your systems or that your nanoparticle is not stable. Right. So what beta potential actually tells, it tells about actually the stability of the particle. So before the beta potential, we should know the electrical double layer, right? So what is that? So how the particle is charged, or how charge is formed. So if you dissolve, or if you just suspended the particle in the solution. So remember, the particle should be suspended in the the diluent or the solvent, then you will get the zeta potential. If it is soluble, then you will get the Nernst potential. That is a different chapter. So if you suspend the particle in the solvent, so the charge present on the solvent, that maybe you have added extra from outside, or if it is a water, simply there will be some H plus and OH minus ion. So it will absorb on the uh, surface of the particles, or if there is any ionization functional group like carboxylate or the amide or amine, then there is a changes from the charges. And another one possible is there, that is if there is a difference of the dielectric constant between the particle and the solvent, then there is a chance to form the charged particle, but that was very rare. So with these charged particles, they are will undergo the Brownian motions, and there is there may be a tendency to the partial sedimental sedimental. So how it will go is, if the density of the particle uh, is too high, if the viscosity or the resistance of the liquid is too low, or if there is a chances to agglomerate or agglomeration tendency of the particle. So what we have to do, we have to stop this agglomeration tendency of the particle, and how we can use this one. We can manipulate the charge by adding the opposite charge whatever you have on the particles. So it can form a this kind of uh, let's say particles, or it have a charge here, and if you add that extra charge, then it will form a another charge layer. And simply for the other particles also, if it is positive, uh, and we will get some negative. So this basically will not come close together. It will not form the uh, aggregate. So and we will get the stable particles. So it will form the double layer actually, which is called the electrical double layer. And another technique, if you increase the resistance or the viscosity of the medium, that means that is steric stability. If you add some polymer on the medium, so it will arrest the movement of the particle. So it will cease the movement, and it will lose the tendency to the agglomerate. So this is another option, another one. And so what we see that two. technique, that is electrostatic charge stabilization. And the static stabilization, we can stabilize the any nanoparticle or the particle system in the suspended form. So with the electrical charge stabilization, it is going to increase the charge around the particle with some additional charge particle or the charge ions, that is sodium hexametaphosphate or the sodium pyrophosphate features. And with static stabilization, you can add some polymer resins, non-ionic substance like that. So this is the scope of our study, that is the zeta potential. This measurement is relevant, very much relevant with the stability check. And this one, it is not in the scope of the zeta potential. It is usually the studied in the rheological study. So, so we know the what is electrical double layer, because we see if any particle is charged, then if you add the additional charges, or if there is any charge ion is present in the system, it will make another additional layer on top of that charged one, and it will form the electrical double layer. So this is the surface charge. This is the primary one, which is known as the Stern potential here. And if the secondary layer, which is the bilayer, actually the difference between potentials between this, which is known as the slipping layer, because this positive charge, whatever it is absorbed on the particle, it is tightly bound. If you move the particle, so it will move along with this charged particle, right? So on that case, what will happen? Whatever the exact diameter was like size was the size is from up to here, but now the size is little increased as it is tightly bounded with the charge. And this layer is called the sleeping layer, because it is going toward pushing that other ions to uh, uh, from one side to another side due to the Brownian motion. And the difference between this potential difference between this layer and this layer is known as your zeta potential, right? So this is the zeta potential. So it is dependent property of the surface charge, and as well as the pH of the solution, ion concentration, and solvent or the non or on all components present in the solution. So in a very physical significance, zeta potential, it basically says the stability of the particles. If someone says the zeta potential is high, that means if this is a two particle, so it will repel from a longer distance. That means its charge will influence to the long to towards the longer distance, and if someone the zeta potential is less, so it will repel uh, not so much longer distance, it will depend from a closer distance. So this is kind of a physical significance of the zeta potential. So usually people use that one so that it not get a chance to came close and to form the aggregate. So before going to the measurement technique, I just give a very quick overview of the DLVO theory. So this theory actually it says the distance between the particles and and the potential difference between them. So what you have, if you have a this kind of two same charge particle, that positive or positive, they will repel, right? If you came, if there is a one particle and if there is another one, if you just uh, to came if you just decrease the distance between them, and if there is a both are the same charge positive one, so it will repel like that, it will go like this, and it is called the V repulsive. And if it is one is positive and one is negative, if you bring them close, so they will attractive, so van der Waals forces the attractions. And the third one, if you bring close the two same charge with a very close proximity, so initially they will repel, and after that they will attract the force. So that is due to the orbital overlap of the two charges. So this will be called the primary minima. And now the another situations on the graph. So like here, so here what is happening? If you have a two charged particle and if you add some external electrolyte, then it will form a kind of electrolyte breeze, like negative, positive, 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 like that. So if you, in that time, what will happen? If you move the particle, it will move the both this one, and along with this electrolyte breeze. So on that case, you will get that one, these secondary minima, and usually this is observed in the flocculated flocuse form. So that is why when people are preparing the flocculate solution or the flocule, so they have to add the electrolyte in a very controlled manner. So this is actually the graph basically says the distance between the particles and the potential difference between them. So usually in aqueous medium, the potential, if it is more than plus minus 30 or the 30 millivolts, is considered uh, uh, sufficient to keep the particle apart, so that it will not aggregate or it will not form. So now, actually, the thing is that how we are measuring the zeta potential. Right. So zeta potential actually measurement is a very complex process. So to get the zeta or the zeta potential, you need to measure the electrophoric mobility of the ions, which is uh, related to the Henry equation, and uh, the and you will get that zeta potential, and the instrument function, the simultaneous function of the applying electric field and the light scattered by the different type of beam, and it further we do the phase analysis to get the frequency, which I will tell in a next few slides. So just remember this kind of term, that SFR or SFR, fast field reversal, slow field reversal. This will discuss. And so for zeta, what we need for zeta potential, we have to measure the electric mobility, and then if you relate with the Henry equation, you will get the zeta potential. So for electrophoretic mobility, you need the velocimetry, the laser Doppler velocimetry technique, and from that, with the phase, with the pulse, you will get the frequency shift. So this is the instrument of design representation. So we have beam splitter. It will split the beam from the same source of light in the two parts, one reference beam and uh, another one, second one goes to the sample for the scattering. So this one and this one, and both beam reaches the APD detector, that is the avalanche photodiode, to the various optics and the optical cable in order to be detected. And this is the Henry equation with the electrophoric mobility and the zeta potential. If we measure this term, that is the electrophoretic mobility, we can calculate the get the zeta potential of the particle, because all other three is the constant, or it can be available. So higher the charge, higher the mobility, and lower the charge, lower the mobility, and you can uh, get the electrophoric mobility. So what we generally do, so this is actually the Malvern patented folded capillary cell, capillary and the electrode. Now, if you just imagine, you just unfold the from here to here, you just unfold this capillary, you will get this kind of arrangement. So when your charged particle is moving towards the opposite electrode, means when you are applying the electric field here or doing the potential difference, then there is a movement of the particle, right? And so this is known as the electrophoresis, and this is actually the signal what we want to measure. But along with this uh, charged particle, there is a chances, or there definitely there will movement of the liquid or the ion, which is known as the electroosmosis, and this is not. So we don't want to measure that. We want to measure only the signal. So what we technique we use for that, we use the entry measurement technique. That is the mix mode measurement technique. So we mixing up the two ways of the electric field to tackle the problem in our in our advantage, right? So what does it mean? So in a entry means that I told that this is the mixed mode measurement. So it is mixing up of the two ways of the applying electric field. That is one is the FFR, so that is fast field reversal. So what we do in the first half of the measurement, we perform the fast field reversal. That means switch the polarity of the two electrode very rapidly, 22 to 25 in in a second. So the particle having the large theta potential get influenced and drag under the electric field. So their mobility and the zeta potential got measured, while noise remain the lowest since the liquid movement is not taken place in this case. So we will receive the zeta potential average value in this manner. So another one, the in the second half, what we will do, it is the SFR, that is slow field reversal. We reverse the electric field once, but the particles are exposed for the longer period. So allow liquid move, the liquid or the ions move, even those particles with no potential at all. So it is chances to move. So we receive their data as well. We get the zeta potential distribution. So if with the and you will come up with this kind of the graph, or the fast forward, the fast field reversal will give this average beta potential value, and the second half, that is the slow field reversal, will give the will give the distribution of the graph. But sometimes if you are measuring the data, you will get only the theta potential value. We may not get the distribution graph. So that is a mental feature, because if you have a conductivity higher than 5 millisiemens, then 5 millisiemens, then it will not perform this slow field reversal. It will get only the average theta potential value. It will not show the size. And uh, now the second one, that how we are we are measuring the frequency shift with the pulse, which is the phase analysis light scattering. The way instrument measure this one is by the laser droplet effect. So this is the equation for the V is the particle velocity, lambda is the laser wavelength, and theta is the scattering angle. So mobility is measured by the laser droplet effect, which actually relates the particle velocity to the frequency shift. So as the particle move actually towards the detector side, there will be increase or change of the frequency. So if this one is the reference one, and the shift over the frequency, and you will see the intensity variation, because the frequency shift measurement is bit of tedious job or the tedious process. So since we are not using any frequency measurement equipment technique, but rather we measure the intensity, and the intensity changes by the APD detector. So let's see that how we are measuring the frequency shift by existing the known technique. So if you just combine this reference beam and the scatter beam, you will see this kind of two-wave interface, that is the constructive and the destructive one. And from that, having a and from this distributivity, so with applying the pulse, that is the phase analytic light scattering, you can get the gradient of that one, and from that you can easily get the frequency. And if you just put the frequency shift on that equation, whatever I yeah, in this equation, you will get the velocity, right? And and you will come up with a it is with this the result. So here you will get the zeta potential value, and as well as the zeta potential distribution, that graph. So if we are actually in the reference beam and the deep beam is combined scatter beam with the reference one, and we receive the constructive and the destructive interface light variation as a frequency carrying particle, and this uh, getting that frequency shift, which is uh, which will give the information of the particle velocity, and you are getting the beta potential when you are feeded that value in the Henry equation. This is the actually the a very quick procedure that how to do the electrophoric light scattering, taking out the measuring the beta potential. The sample is placed in a capillary, that is a folded capillary, and electric field is applied. The charged particle are attracted to the opposite charge electrode, like here you can see, and the laser beam is passed through the sample in the capillary cell, which undergoing the electrophoresis.
हाँ सर डिस्क्रिप्शन देना है वो
These particle the frequency shifted, and this frequency shift is directly proportional
जैसे उसमें मुझे हटाना भी था उसमें मैं समझ
to
दिखाता नहीं
particle, and this electrophoric mobility you are adding an Henry equation, and you are getting the zeta potential. There is a lots of application of the zeta potential for the compatibility of the mixed component chemistry. It is also effectiveness for the surface charge modification of the coating industry. It predicts the stability, particularly the the charge stabilization, absorption, an indicator for the stability. It also we can get the isoelectric point information. It gives also the acidity and the alkaline salinity of the materials. So in the multi-component products, so the film formation, the emulsions themselves, and the additive in the formulation can easily be monitored with the zeta potential. Each component you can get. This is one example of the variation of the zeta potential with the surface activity of the surfactant. But cationic, this is anionic surface, and on that, the absorption of the catalytic charge substance with a carbon chain length from it is varying from 6, 8, 10 to 16, and see there these are beta potential one. The coating difference, the coating defects. Sorry. So the variation of the beta with a coating defect, that is also the study for making for see the less defect on the surface, and this is a coating efficiency uh, measurement with the graph of the coating efficiency versus beta potential. You can see that one by the beta potential how it is changing. So in the summary, that zeta potential studies are very important for multi-component or the formulated products, cosmetics, mainly paints, or in the brightness or the absorption of the light, drug delivery or emulsions. In a broad scale, if I say, that is a water treatment, paper, ceramic or refractory, the large scale production examples in vaccines, virus, bacterial studies. Now they are extremely useful. The zeta potential provides the information about the interfacial region of the product. It is effectiveness of the surface charge, predict the stability, and that's compatibility for the mixed component chemistry, that emulsions or other formulation products. So this is all about the about that beta potential and the size and other key acronyms, whatever I told, the means, MATLAB, FSR in three parts. So besides this, another one of the advantage features if you have that was with the beta surgery is that molecular weight measurement with some limitations. So before going to profit, I just make point out this thing that is a it is not the exact technique, but as the feature is there, so you can try that one, but with some limitation. So it is very well known that the total scattered intensity by the uh, uh, scattered intensity by a molecule or a group of molecules in a solution, it depends upon its molecular weight, and the number of molecules in the solution means the concentration, and this uh, have a relation with the I versus varies with the molecular weight in the into the concentration. And if you just simplify these equations with the with this Rayleigh ratio and optical constant, or this p theta angular momentum, you will come up with this kind of uh, this, come up with this kind of uh, formula, and and if you just simplify that one, we will get a y equal to c plus mx kind of straight line. So so and if you can able to perform this graph represented here, you see, and here the intercept and the slope is actually by running the 5 or 6 samples on the samples, and this intercept is related with the molecular weight. That molecular weight equal to 1 by intercept, and that secondary coefficient will get the slope of the slope of the flow plot. So the technique to provide a molecular weight is a molecular weight is a very narrow distribution. So as because this technique will give you one single molecular weight, that is in W. So if you are familiar with the polymer chemistry, so you can know that weight average molecular weight, number average molecular weight, Z average molecular, that is a lots of type of molecular weight is present there, but with this technique you will get the NW1, but for that is as it will give you only a single number. So for very narrowly sized molecule or the narrow distribution molecule, it will give that one. But for broadly sized molecule or the broad distribution, it is not suitable. So for polydisperse sample, that is, you do not get a linear equation on points, and correlation score is very poor. So just because of the heterogeneity of the mixture of the molecule when it exposed to the laser light. So because as there is a polydisperse means there is a different size of polymer, so you get the fluctuating light intensity concentration. So for that, actually, they have different. We have a different techniques, that is the gain permission chromatography. The RIL detect light scattering. You will get a full distribution, and with the same equations, you can get the molecular weight of the each component, each detailed characterization properties. So these are the few conditions for the molecular weight calculation with that SLS method. So it should be complete resolution. It should be narrow size distribution, low polydispersity. It should not be very broad one. The size must be
Okay, Dr.
partly.
Dipanjan,
Yeah.
I think we should stop here.
This is
We
the
have
last slide
2 minutes
actually.
only. Okay,
This
thanks
is
for
the
your nice
last slide.
presentation. And I have one question.
Mhm.
Up to what pH we can do zeta potential?
One minute. Hello. Yeah.
Yes, up to
Hi,
what pH we can do zeta potential? Higher
hi,
side for.
uh, hi, Sudhir sir. Hello.
Yes. Hello.